Hello, welcome back. Right. Okay, so we're still on basic concept in chemical combination and of course calculations. So now I have mole. We're gonna be looking at mole concept. Okay. Now, what is a mole? Now, a mole is a number that contains as much elementary entity or particles as Avogadro's number. All right. So now we actually use a mole to designate, right? We use a mole to designate the number of particles or even the number of atoms, okay, that is in a substance. Now, so since we now know that a mole contains as much elementary entities or particles as Avogadro's number, the question is, what's Avogadro's number? Avogadro's number is equal to 6.02 times 10 raised to the power 6 particles. Okay, now this Avogadro's number is used to designate the number of particles contained in 1 mole of a substance. Now, particles here can be atoms, it can be ions, okay. It can be even be molecules, right? Because you know that a substance is made up of particles, right? So in form of atoms, ions, or even molecules. Okay. So now the same. Okay, let's illustrate this. Okay, in a very simple term. All right. We actually use mole to actually represent this number of particles. Okay, so we simply mean that if we want to measure a substance, we measure it based on mole, right? Not based on the just the particle, one particle, right? We measure it collectively, right? Because 1 mole have this number of particles. Now, for instance, let's say you want to measure rice. You don't measure rice by just 1 grain of rice, okay? If you want to measure rice, you measure it in cup, and 1 cup contains many grains. The same thing with atom. Atom is too small, excuse me, okay, that you can't just measure it by just one atom. You can't measure, atom is too small, okay, that you can't measure a substance by just uh the number of atoms by just one atom, okay, but you measure it in group of atoms, and that group, okay, which of course which contains Avogadro's number is known as mole. So for every, you should take note that 1 mole of any substance will always contain 6.02 times 10 raised to the power 23 particles. All right, 1 mole of every substance. So that means 2 mole is going to be 2 times 6.02 times 10 raised to the power 23 particles. So please take note of that. Let's see a typical example where you need to convert. Okay, so let's look at the relationship between mole and Avogadro's constant. Okay, so number of mole is Avogadro's constant divided by number of particles. Okay, I just want to see this relationship, whether it's okay, this is what if 1 mole, all right, also is equal to, excuse me, if 1 mole is equal to 6.02 times 10 raised to the power 23 particles. All right, so invariably now, if I have 2 mole, okay, 2 mole will be equal to 2 times 6.02, all right, times 10 raised to the power of 23. So that means the number of moles is gonna be the number of particles, okay, is gonna be the number of mole times Avogadro's constant. So number of particles, okay, so the formula is number of particles of a particular substance, all right, can be measured by the number of mole, okay. Okay, I can just use amount, the amount, okay, in mole, amount in mole, the amount of that substance in mole, or the number of moles, okay, number of particles, okay, is is gonna be measured as number of moles okay, then now multiply by 6.02 times 10 raised to the power 23. So that's the relationship. So from this formula now, if you want to get the number of moles now, all right, the number of moles now can actually be given as, if you want to get number of moles, that's going to be number of particles all right, then divided by the Avogadro number, which of course is 6. Avogadro number, right? Alright, so now I think let's look at typical example. For example, how many particles are contained in 2 moles of a substance? So simple. So number of particles, okay. Number of particles that you can get in 2 moles of a substance is just gonna be 2 times, all right, 6.02 times 10 raised to the power of 23. Okay, so that should be 12.04, right? Times 10 raised to the power 23 particles. All right, so now, okay, so now we'll look at another concept, which is molar mass, right? Now, the molar mass is defined as the mass of 1 mole of a substance. Molar mass is evaluated the same way formula mass is evaluated, all right? So the same way we calculate formula mass, molecular mass, that is how we also evaluate molar mass, right? Okay, so I think we'll proceed. Now let's now look at the relationship between number of mole and the molar mass. Okay, number of moles. If you want to get the number of moles of a substance, okay, its relationship with molar mass is that number of moles is always given as mass, the mass of that substance, okay, then divided by the molar mass. The mass of the substance divided by the mass of 1 mole, which of course is the molar mass, right? That's how you get the number of mole of the substance. So I can use symbol, I can use small letter m, mass of the substance, all over each molar mass, capital letter M. Okay, so please take note of that. So number of moles is mass all over molar mass. Now, for example, let's look at a question. What is the number of moles in 6 grams of water molecules, right? So number of moles for 6 grams of water molecule, so the mass is 6, right? Then divided by the molar mass of water molecule, right? Water molecule, we calculate the molar mass. We've already done that before, right? Water molecule is H2O. So the molar mass is going to be 2 atoms of hydrogen. That's 2 times 1. Atomic mass of hydrogen is 1, okay? Then plus 16, right? Atomic mass of oxygen. So this is going to be equal to 6 all over 2 plus 16. That gives me 18. Okay, so use calculator and you're good to go. Now I've solved that already. Okay, so the solution, so the answer is 0.33 moles. All right, so next concept. So we'll be talking about percentage composition. Okay, or percentage by mass is something. Now, percentage composition or percentage abundance of element in a compound, it is percentage by mass of the element in that present in that compound. Okay, so if we have a compound, all right, that has, let's say, different element. Let's just take, for example, COCO3. Okay, it is called that this compound contains three elements: carbon, calcium, carbon, and of course oxygen. All right, so they have their different composition. There's a percentage of this of each of these elements, okay, present in this compound. That is what, okay, we mean by percentage by mass. So the percentage by mass of each element, okay, in this compound is what is regarded as percentage composition. For example, now if you are being asked to, okay, what is the percentage by mass of oxygen? So to do that, simple. Percentage by mass of oxygen is simply going to be the mass of the oxygen. Oxygen has three atoms here, okay? So the mass of oxygen is going to be 3 times, okay, 16, then divided by the mass of the entire compound. Mass of oxygen divided by the mass of the entire compound. The mass of the entire compound, of course, the mass of carbon here, please pardon me, mass of calcium is 40. Mass of carbon is 12. Of course, the 3 times, please pardon me, 3 times 16. Then, of course, in percentage, you need to, it's expressed in percentage, you need to multiply by 100. Okay, so this should be 48 all over 100. Okay, can just calculate that times 100. So the percentage by mass of oxygen in COCO3 is simply 48%. I hope that is well understood. Okay, so I think we'll just so percentage by mass of that element divided by mass of the compound times 100. That's what I just illustrated. So let's look at example. Probably I'll solve this one. Okay, so we're looking what is percentage composition of oxygen in the following. So I've calculated the CaCO3. Let's look at this H2SO4. Okay, H2SO4, which we know very well that is made up of 2 atoms of hydrogen plus 1 atom of sulfur plus 4 atoms of oxygen. Okay, so percentage by mass. It's going to be equal to the mass of the oxygen, right? 4 times 16 divided by the mass of the entire compound. 2 times 1 plus sulfur is 32. Then of course 4 times 16 times 100. Okay, so I believe you can do this. Okay, so that's just it. That's just it. So that's just how to evaluate that. I'm sure it's just a very simple thing to do. Let's look at that of aluminium. Okay, the aluminium tetrasulfate 6. That one seems somehow aluminium tetrasulfate 6. Okay, it's written. This is the formula, right? So you see this one kind of seem complex because there's a bracket and there's a subscript. But first of all, let's separate it. Okay, so this is actually made up of 2 atoms of aluminium. Then of course 3 atoms of bracket open sulfur plus 4 atoms of oxygen. So let's open this bracket now. So 2 atoms of aluminium, it's going to be 3 into, then that's going to be plus 3 atoms of sulfur, then 3 times 4, that's going to be 12 atoms of oxygen. So with that now, percentage by mass. Percentage by mass is going to be equal to, all right, 12 times 16, right? Divided by 2 times aluminum is 27 plus 3 times sulfur is 64 and plus 12 times 16. Okay, so that's 100. So take your time. Take your time and actually work on that. All right, so moving forward. So now let's talk about the formula of chemical compound. Now the formula of an inorganic or all chemical compound, okay, is actually divided into, though for inorganic compound there is more, right, but more division of its chemical compound, right, but for generally formula of chemical compound is divided into empirical formula, right, and molecular formula. So now what's empirical formula? Now empirical formula is the simplest formula of a chemical compound. So what empirical formula show us is the element present in that compound and their mole ratio. So that's the only information that empirical formula shows, okay? The element present in the compound and the mole ratio, the ratio of the elements. For example, if I said that the empirical formula of an organic compound is CH2, what if this information is just telling me that in this compound actually contains hydrogen and carbon, all right, in the ratio of 1:2? That's just this mole ratio, okay? So it is not telling me the actual number of atoms of carbon, neither the actual number of atoms of hydrogen, but just the ratio of their combination, okay? So that's basically, so it's the simplest formula. Empirical formula is the simplest formula. So we simply means that you need the simplest formula, empirical formula, before you can actually get, okay, the actual formula, molecular formula. Once you got an empirical formula, because every molecular formula is actually built from empirical formula, okay? So the simplest unit of the formula of a compound is actually the empirical formula. So I hope that is well understood. Okay, so for example, CH2 is empirical formula of a compound containing carbon and hydrogen in the ratio of 1:2. I've talked about that, okay? Now, question is, how do we evaluate empirical formula? Because for us to actually even get the molecular formula of a compound, we need its empirical formula. Now, to evaluate empirical formula, we need to find the mole ratio of the element in the compound. So simply, all you just need is just get that mole ratio and you have got an empirical formula. So the question, what is the formula for mole ratio? Okay, so mole ratio is actually evaluated by the simple formula. Mole ratio is mass all over molar mass, simple. All right, use mass all over molar mass, or you use percentage by mass. That's two way of actually evaluating mole ratio, okay? So for you to get mole ratio of each of the or each of the elements in that compound, okay? You can do mass, if the mass was given, divide mass by molar mass, okay? mass all over molar mass. So this will actually help you to get the number of mole of one and the number of mole of the other. So in that case, that becomes the mole ratio. Or in most cases, okay, to get mole ratio, you use the percentage by mass. Percentage by mass of that particular element, then all over molar mass. So okay, this one is very common. That's an example here. We could actually do justice to this, okay, using an example. Now the question goes like this: an organic compound contains 72% of carbon, 12% of hydrogen, and 16% of oxygen. So which simply means that this organic compound contains carbon, hydrogen, and oxygen. So the question is, find the empirical formula. So I need to get the mole ratio of these three elements. So I need to arrange it, okay, in order. Carbon, hydrogen, and oxygen. So I need their mole ratio. All right. So mole ratio. Mole ratio is okay. So of course, by mole ratio, we know that we use the formula percentage by mass all over molar mass. Okay, so percentage by mass according to the question of the carbon is 72%. Then divided by the molar mass of carbon. Of course, you know that atomic mass of carbon is 12, right? Then hydrogen is 16%. I hope I'm not mistaken. The next is hydrogen, yeah, 16%. No, 12%, please pardon me. Hydrogen is 12%. Atomic mass of hydrogen divided by the atomic mass of hydrogen, which is 1. Then oxygen is 16%. Right? So I hope calculator will help us do that. 72 all over 12. What do we have, sir? I'll need a calculator. I don't want to stress my brain, so I will definitely need a calculator. So I got a calculator. Here we go. Okay, 72 divided by 12. 6. Okay, so this 6, this 12, this 1. Okay, so the next is I would have divided by the smallest mole ratio if it is not, if it has, this ratio have not been reduced to lowest term. Okay, the ratio must be reduced to lowest term to 1 before I can use it. Now since I have one of the ratio being reduced to 1, so I don't need to divide by the smallest mole ratio. So that means my ratio is 6, 12, 1. So in that case, now the empirical formula. Alright, it's gonna be equal to, alright, carbon, 6 atom of carbon, that's 6, 6. 12 atom of 12 atom of hydrogen, H12, right? Then 1 atom of oxygen, just O. So this is the empirical formula of that compound. I hope that is well understood. Okay, so we cannot talk about molecular formula having non-empirical formula. What is molecular formula? Now, molecular formula is the actual formula of a compound. It tells us the actual number of atoms of different elements present in that compound. Okay, so the actual. Now, how do I actually get molecular formula? Right. Molecular formula is actually is gotten by evaluating the multiple. Molecular formula is actually the multiple of empirical formula. So if I multiply empirical formula by some number, then automatically that empirical formula is converted to molecular formula. So to convert empirical formula into molecular formula, we multiply by a subscript n. All right. So look, this is a simple formula. Molecular formula is equal to empirical formula multiplied by the subscript n. So once we get the subscript, multiply the subscript by the empirical formula that you have evaluated, you have automatically converted it to a molecular formula. Now the question is, how do we get this subscript n that I need, okay, to convert empirical formula to a molecular formula? Now this is the formula for the subscript n. To get this subscript n, we need is going to be equal to molar mass of the molecule. That particular molecule we want to evaluate its molecular formula, right? We need to get the molar mass. Then we now divide by the molar mass of the empirical formula of that particular molecule. All right. So I think it will actually make sense if I go by example. Here is a question. Question goes like this: a compound contains 40% of carbon, 6.7% of hydrogen, and 53.3% of oxygen. If the molar mass of the compound is 180, find the molecular formula. Okay, so this will be your question. So simple. The very first thing I should do before I get to find the molecular formula is to get my empirical formula, right? Let me clean up. All right, so this compound, as usual, is made up of CH and of course O. Okay, so I need to get their mole ratio. So remember, I need mole ratio for me to. So what is the mole ratio? Okay, percentage abundance of carbon is 40, so that's going to be 40 divided by 12. All right, that of hydrogen is 6.7, so I'm having 6.7 divided by 1. Then oxygen is 53.3, so I'm having 53.3 then divided by 16. Alright, so let's start our divisions. 40 divided by 12 is 3.33. 3.3 approximately. Okay, 6.7 divided by 1 gives me 6.7. 53.3 divided by 16. 53.3 divided by 16. 3.3 again, right? So this time around, I'm not using this. Okay, I have to divide by the smallest mole ratio. All right, I have to reduce to the lowest. Every ratio must be reduced to the lowest term. Okay, so divide by the smallest. The next step is divide by the smallest. So the smallest here is 3.3. So I'm dividing this by 3.3. I divide this by 3.3. And of course, I divide this by 3.3. Alright, so if you divide, you have 1, alright, is 2. This is approximately 2 is to 1. So, empirical formula. Alright, is going to be equal to 1 atom of carbon, 2 atoms of hydrogen, 1 atom of oxygen, CH2O. Alright, so now remember, for me to convert this empirical formula to molecular formula, I need to multiply the whole of this CH2O by an unknown subscript n. Alright, so the question was the n. The n is going to be equal to the molar mass of that molecule. Now the molecule, according to the question, has a molar mass, okay, molar mass of 180. Okay. All right, and then divided by the molar mass of the empirical formula. I have to divide it by the molar mass of the empirical formula. The empirical formula is CH2O. So that's 12. Molar mass of carbon is 12. Then 2 times the molar mass of oxygen. That is 2 times 1, 2. Then plus, okay, the molar mass of oxygen, okay, of oxygen here. So this is going to be equal to 180 divided by, all right, this is 14 plus 16, and that should be 30. Okay, yep. 180 divided by 30. That's 6. So now molecular formula now. It's going to be equal to, bracket open, C H2O, then multiply by 6. So that's going to be C6. 6 times 2 is 12, H12, then O6. All right, so that is it for molecular formula. Okay, so let's proceed. Now we're going to talk about valency. Okay, what's valency? Valency is the combining power of an element. Now, for an atom to combine with other atoms to form a compound, there must be a mole ratio at which this is done. Okay, so every combination has mole ratio. Okay, so this mole ratio is determined by valency. So the valency of the atom coming to combine, especially in a ionic bonding. Mostly we actually regard valency when it comes to ionic bonding. Okay, ionic bonding is a bonding where there's a transfer of electron between metal and non-metal, right? So valency of a substance depends on the number of valence electron. Okay, electron at the atmosphere, valence electron is electron at the atmosphere. So for you to be able to measure valency, you need to know the number of electrons at the atmosphere of that atom. So thus we can write the correct chemical formula of a compound knowing the valency of the atoms in a compound, right? Okay, so let me illustrate that. So for you to actually write for chemical formula, and of course all this time I have actually been giving you formula, right? I just give you the formula, and I'm very sure you ask yourself how do one write formula correctly without cramming it, because you don't need to cram formula. For example, if I ask you to write the formula of magnesium tetrasulfate 6, okay, so most times students want to cram it, okay, maybe you've seen it before, you want to write it, but that is, don't need to cram it, okay. It has a formula to which, all right, we can, which we employ to write those chemical formula, right? So now, let's see how that works. Okay, look at how it works. If I have a metal, right, that has a valency is this is where we write valency. At this point, if I have a metal that has a valency of X plus combined with another metal that has the valency of Y, then if I want to write the formula of these two, right, it's gonna be equal to gonna be A. Y comes as a subscript. This Y, there's gonna be interchange of valence, right, to the subscript. So I'm gonna have AY, then BX. Okay. So, for example, sodium has valency of +1. Let's say sodium combined with oxygen, one atom of oxygen with valency of 2-. Okay, So if you are being asked what's the formula of sodium oxide, there's going to be a change in valency. 2, all right? This 2 comes here as a substitute, then this is 1. 1 come to the other side. Okay, so that is why the formula of sodium oxide is Na2. But the question is, how do we actually get this valency? Let me show you how we get the valency. For example, let's take sodium for an example. Okay, the number of electrons, sodium has 11 electrons. Sodium has 11 electrons, right? So these electrons, you know that you can divide them in shells, in which for sodium, okay, the electronic configuration, the inner shell has 2 electrons, the outer shell has 8 electrons. Okay, we'll still treat this when we treat atomic structure. Then of course this is 10 now. Then the 1 electron goes to the atomos shell. So sodium has 1 atomos shell electron. That is why sodium, okay, has the valency of just +1. Why is it plus? Because any atom that have no electron, valence electron from 1 to 3 have the tendency of losing it, and once they lose those electrons, they become positively charged. While atoms that have electrons from let's say 4, or better still from 5, 6, 7, all right, have the tendency of attracting electron to themselves, and once they attract electron to themselves, they become negatively charged. Okay, so please take note of that. So I would probably love to write another one. Okay, so let's look at magnesium. Magnesium has 12 electrons. Okay, so these 12 electrons have these 2, 8, that's 10 now, then the 2 at the atomos shell. So magnesium, okay, has a valency of 2 plus. Let's look at chlorine. Chlorine has 17 electrons. All right, 17 electrons. Okay, so dividing this, this is going to be 2, 8, then 10. This the 7 here at the atomos shell. So chlorine needs 1 electron to complete it. All right, so chlorine is a non-metal, and it needs to accept 1 electron to make it 8. All right, so for the fact that chlorine needs to accept 1 electron, its valence is going to be -1, just minus, Cl minus. Okay, so now a reaction that involves the coming together of magnesium, which of course is 2 plus, and chlorine -1, we actually yield a compound, okay, in which I will have Mg, the one Mg1, okay, which is something as Mg. Then of course 2 come to this other side and become a subscript, then Cl2. So this is how we write valency. Okay, you can probably look up more examples. So those are valency. Okay, so writing chemical formula using valency. To write chemical formula of ionic compound using valency, we simply exchange the valence to subscripts. Okay, I've actually talked about this. All right, we exchange valency. Now let's look at example. Write the chemical formula of the following water molecule. Okay, of course we know very well that water molecule is made up of hydrogen, and so hydrogen has 1 electron, so this the valence is +1. Oxygen, all right, remember oxygen here has 8 electron, so if you divide it, that's 2,6. So oxygen needs 2 to complete, so oxygen is 2 minus. So that's why when they combine, you're gonna have H2O. Let's look at another one. Magnesium chloride, I've written that one. Then aluminum oxide. Okay. Yeah, still the same. So we can proceed. Now we'll talk about radical. Okay. Now a radical is a group of atoms that is regarded as a unit. So a radical is made up of more than one atom, but they actually they are considered as a unit, as just one entity, and that's why they are called radical. Okay, so why? Because they are called radical because they share a single valency. So the valency of the radical is just gonna be shared by all the elements of the radical, right? Okay, let's look at a typical example. Now, it is most of these radicals are in form of uh, positive ion, negative ion. For example, that's what is known as hydroxide ion. Okay, this is actually a radical. All right, call this hydroxide ion. This is an ion too, negative ion. Teratososulfur ion. This is a radical. Okay. There is we also can also have CO3, right? 2 minus. Triazocarbonate. Those are radicals, okay? etc. So these are radicals, okay, have common their valency, they share common valency. Okay, because this is made up of oxygen and hydrogen. So this valency belongs to all of it. Then sulfur and oxygen, this valency. So now a situation where you have okay positive ion reacting with radical, all right. Let's look at this example. You know very well that what will be formed, all right, is gonna be Na2SO4. Okay, so that's what they call it ionic compound. Right, positive part of this is the positive part of it, and this is the negative part of it. Okay, so for example, let's say you have magnesium, all right, which of course is 2 plus, reacting with CO3 2 minus. So two, if two they have both of them have two, okay, if I break down the ratio, that's going to be 1:1. All right, so at the end of the day that's just going to be MgCO3. So I hope that is well understood. All right, so now let's look at IUPAC names of a chemical compound. Okay, as the name, this IUPAC is an abbreviation of International Union of Pure and Applied Chemistry. Okay, so they have devised method of actually naming both organic and inorganic compound. Right, now their method of naming, okay. Now let's read this. Generally, there are two types of inorganic compound that can be formed: ionic compound and molecular compounds. Okay, so nomenclature is a process of naming chemical compound with different names so that they can be easily be identified as separate chemicals. Okay, so let's look at some name. Let's look at name of compound between metals and non-metals. Right. So sometimes you may be asked to, you may be given the chemical formula. Okay, so that the chemical formula for you to actually name. How do you name it? Now, this example, CaCO3. How do you name CaCO3? All right. Now, some people will, okay, they actually name this mostly because they actually crammed it. Okay. Now, this is calcium triazocarbonate 5. Okay. Now, I might actually be mistaken whether it's triazocarbonate 4, 5, or whatsoever. So the question is, okay, I believe that you should ask that number at the end of the name. Where does it come from? First of all, if you want to name this compound, remember this compound is actually made up of metal, the positive ion and negative ion. Calcium here is the positive ion, while the triazocarbonate is the negative ion. All right. So if I want to name, I have to start with the positive ion. So I have to start naming. Okay. I have to name the calcium first. Excuse me. All right. Then I now go to this. Now, if it is a radical, all right, especially a radical that contains um uh some number of atoms of oxygen, like CO3 is a radical. So I will start by naming the oxygen, okay, right, that is attached to the oxygen. That's why I have calcium. Okay, now this entire radical, okay, is triazo. Why? Because why triazo? Because the oxygen there is 3 atoms, triazo. So before I now come to name this carbonate, all right. Now the question is the 5 I actually mentioned, okay, which probably I need to know whether it's 5 or 4. Where does it come from? That 5, okay, is actually the oxidation number of carbon. All right. How do I actually get the oxidation number of carbon? We'll still treat this, okay? To get to know the oxidation number of carbon in this particular compound, okay, is simply I'm going to write the valency of each one of them. All right, then I find the oxidation number of carbon. Right now, the oxidation number of a compound, total oxidation number of a compound, is equal to 0. So the oxidation number of calcium already we know is +2. That is the valency. What I mean by oxidation number is the valency. Okay. Now I want to the oxidation number of carbon. That's what I'm looking for. Then plus the oxidation number of oxygen. Oxidation number of oxygen is -2, right? Then of course I have 3 atoms of oxygen. I multiply by 3. Is equal to 0. Okay. So this is gonna be 2 plus C. -2 times 3. That give me. What does that give me? Okay, that's give me -6, right? Okay, so you see now, that's a mistake now I made, okay, by saying 4, because by saying 5, it is 4. So that is I don't need to cram. All I need to do, if I'm not sure, all right, I have to use this. Okay, so with what I have here now, I'm gonna have 2 minus 6, that's 4. I have C minus 4 is equal to 0. Okay, so C now is gonna be equal to 4. So that is why I can now name this as calcium triazocarbonate 4. Why? Because the oxidation number of carbon in this particular compound, having evaluated it, is 4. So that is how we name compound. All right, so let's look at the other name. All right, here. The same procedure. First of all, I will name this sodium. Then this is now going to be triazo. Triazo, then this nitrate, okay? Triazo nitrate. Then what's the number? What's the oxidation number of the nitrate? Okay, 5. We'll confirm. Let's confirm, all right? Sodium here is +2, right? Of course, we've done that of also O3. That's -6. Sorry, sodium here is +1. Please pardon me. Sodium is +1. So that's 1 minus 6, that's 5, all right? That's minus 5. So N is equal to 5. So that is why is nitrate 5. Nitrate 5. Okay, so that is how that is. All right, you can try this. Okay, so let's proceed. So I have more example. Give the IUPAC name of each of these following salts. Now, this is sodium, okay, ozochlorate. So sodium ozochlorate, then the oxidation number of chlorine in this compound. That's exactly what the number will be. Ozochlorate, whatever the oxidation number, okay. So this one is magnesium hydrogen triazocarbonate 6. Magnesium, then hydrogen triazocarbonate 6. Okay, so that is it. So we will return, then we will talk about the laws of chemical combination. The laws of chemical combination. All right, so see you in the next video. Thank you very much.